So what we're going to go over today, okay, is the properties of compounds. We're going to be looking at the properties of ionic compounds and the properties of molecular compounds. And when I say properties, I mean in general their physical properties. We'll talk just briefly about their chemical properties, but for the most part, we're going to be focusing on their physical properties. Okay. Now, you guys learned about physical and chemical properties in junior high. Okay. Physical properties are the things that are readily observable about that material. You don't require any other materials realistically to see these properties, with the exception of if you're testing its solubility, then of course you would need water, right? But for the most part, these are things that are readily observable about that thing, about that material, without having to react it with anything else. Once you're talking about reacting it with other things, those are talking about chemical properties. How does it behave when it's mixed with this? How does it behave when it reacts with that? Okay, those are chemical properties. So we're going to learn the properties of compounds. We're going to look at, obviously, like we said, ionic and molecular. That'll be a big focus because in our lab next week, you are going to get about a dozen unknown compounds. And you're going to have to identify them. Okay? I'll label them in beakers like A through J, or K, whatever the 12th letter is, I can never remember. Okay? So it'll be labeled like A through J, and then what you'll have to do is look at their various physical properties. Okay, check some of their physical properties and see what are they, and then match them up to the possible identities list that I will give you. Okay, so I'll say, one of these compounds is hydrogen chloride. One of these compounds is, or one of these materials is water. One of these materials is alcohol. One of these materials is table salt. One's sugar. Okay, all that kind of stuff. And what you're going to have to do is run essentially the same battery of tests on every substance to determine its physical properties, and then match those physical properties up with the material. So what we want to go over today is, what are some of those properties? What are some things we should be looking for in an ionic compound, in a molecular compound, in an acid, in a base, things like that. All right, so those are things you'll want to make note of, okay? Because as it says here in the second point, understand how these properties can be used to identify a compound, which will be useful when you're designing the procedure for your lab, which you guys will be doing. Okay? Some of the labs we do in this course are cookbook labs. Okay? That means you follow my procedure to the letter and everything goes tickety-boo. Okay? And sometimes you make up the procedure. Okay? Now, I'm going to help you with that this time. I'll tell you what tests and things like that you're going to want to run, but you're going to have to write up the instructions themselves. All right. Questions so far? All matter has certain properties, okay? Some are chemical, reactivity is an example, and some are physical, things like color, density, melting point, okay? Conductivity, ferromagnetism, solubility, okay? Things like that. All these things are physical properties. Color, texture, okay? All that stuff, okay, is all physical, are all physical properties. They're things that are readily observable about that material without anything else around. Okay? Those properties can be used to distinguish between the types of compounds. And when I say types of compounds, I basically mean ionic or molecular. Okay? There are some very different behaviors about ionic compounds versus molecular compounds, and it has to do with what we talked about before, which is in an ionic compound, the bond is very weak, the electrons are traded, whereas in a molecular compound, the bond is very strong, the electrons are shared. That influences how they behave in certain physical ways. All right, so properties of ionic compounds. Okay? Ionic compounds typically exist as crystalline solids, otherwise known as salts, okay, at room temperature. They have very high melting points, usually several hundred degrees. Okay? So they are crystalline solids. Now, are there some molecular compounds that could be crystalline solids? Yes. Sugar is a molecular compound, and it's a crystalline solid, okay? But it's got some other things that are definitely molecular behaviors that salt or other molecular compounds would not, or ionic compounds, sorry, would show. Okay, so they have very high melting points. We're not going to be testing melting points. It would be great if we could. Okay, when you go into university, I mean, they probably have a way better way of doing it now. But when I was in university, they had this, basically this heating apparatus. It looked like a toaster. Essentially it was. And what you would do is you would take like one crystal in a glass tube of this stuff, and you would put it in the machine, and then you would look in it, and it would have this little magnifier. You could peer through with one eye, okay, and you'd watch. Okay, beside the tube was a thermometer, and you would watch the thermometer and the crystal. And when the crystal started to melt, you recorded the temperature, you had the melting point. We don't have that equipment here. It's highly unnecessary for what we're going to be doing, okay? But that was one of the things you had to do in order to see how pure the stuff you had made was, and you got marked on the percent purity, okay, that you got out of a lab, which is why I didn't do very good in chemistry. Okay. All right. Ionic compounds will conduct electricity in solution. That's crucial. They all do that without exception. Okay? If you have a solution that is a compound mixed in water and it conducts electricity, okay, you have an ionic compound in there. Right? The reason for that we talked about before. When you put an ionic compound in water, it splits. Okay, the bond is weak, they split, and you have charged particles. So if I put salt in water, here's a bunch of the salt molecules that haven't dissolved yet. Okay, but once they start to dissolve, I've got sodium over here surrounded by water molecules. That's what these Mickey Mouse looking things are. Okay, positively charged sodium ions and negatively charged chlorine ions floating around in the solution. If I've got positive and negative charged particles, they will allow electrons to flow through the solution. Right? A molecular compound won't do that because when I put it in there, it might dissolve, but it's not going to split. Okay? It's not going to split into positives and negatives, so it won't conduct. Everybody follow me there? Now, I say won't conduct. Does that mean it won't, like, completely won't conduct, or it'll be a very poor conductor? Usually it's very poor. You almost never get something that's perfectly pure. Like the water that we use, it's supposed to be pure water. It's not distilled, but it's supposed to be essentially pure. But it always has some small amount of stuff in it. Okay, and that can happen even when you're transferring it from the container it's in to your container. If there was anything in your container, if it wasn't perfectly clean, you could get some ions, charged particles in there that can interfere slightly. I'm going to keep that in mind. That could be a source of error, okay, for you in your experiment. But usually that kind of stuff happens. So if you get like a 1 or a 2 or a 3, that's essentially non-conductive out of 10. Okay? If you get an 8 or a 9 or a 10, you're looking at an ionic compound. Okay? That's a highly conductive one. Everybody follow there? Okay. All right, and that's again due to the nature of the positive and negative ions that make them up. So if you looked at an ionic compound magnified, you would see the individual crystals. Okay, up close. And each individual ionic compound has kind of a distinct crystalline shape. Their crystals look different. Okay, I can't remember what particular compound that is, okay, but their crystalline structure is unique. Okay, some of them are colored. Okay, nickel compounds like this one are green. Okay, so it's a crystalline solid, but it's green. Okay, if it looks powdery, it's probably still crystalline. Just the crystals are really, really small. Okay, the bigger the crystals, the more grainy it looks. And I generally try to pick stuff that is large and very obviously crystalline in nature. All right, many ionic compounds have not only salts that are brightly colored, but when you put those salts in water, the solution becomes brightly colored, or at least somewhat colored. Right? I mean, generally, if you dissolve something blue in water, it colors the water blue. Okay? If you dissolve something green in water, it colors the water green. So if I'm looking at, okay, these ones in particular will be very useful. Copper compounds generally have blue salts and thus blue solutions. Okay? Nickel compounds are green salts that produce green solutions. And cobalt compounds are reddish salts that produce reddish pink solutions. Okay? Now, does that mean that if you look at a salt and it's red, you automatically assume it's cobalt? It's a safe assumption, but you can't just go, well, it definitely isn't, do no other tests. Okay? You would definitely want to do other tests to confirm, because I could have just been a jerk and taken some sugar, added food coloring to it, and then left it out and waited for it to recrystallize, and then I'd have red-colored salt crystals, or sorry, sugar crystals, and then you'd be wrong. Okay? I'm not going to do that, by the way, but okay, that's something that could happen, so we would still want to run through all of the tests, like check its conductivity. Does that red solution that it made conduct electricity? Well, then it's definitely an ionic compound, things like that. Okay? These ones, though, you'll definitely want to make note of because they will help you to make some of your first identifications on Monday. All right, but like we've said, the most important test that will separate your molecular compounds from your ionic compounds is conductivity. Okay? Conductivity tells you 100% of the time whether it is ionic or molecular. All right, molecular compounds. They can be solids, liquids, or gases at room temperature. Remember, ionic compounds were all going to be solids, crystalline solids in particular. So if you're looking at something and it's not crystalline, it's probably not ionic. Okay, pretty good bet. If it's a liquid, it's definitely not ionic. Right? So if your sample is a liquid, and I haven't told you it's a solution, I've told you it's a pure substance and it's a liquid, you can eliminate then all of the ionic identities from the possibility for that particular compound. Agreed? Okay, so that's an important one to know. Okay, molecular compounds can be solids, liquids, or gases at room temperature. We won't have any gases in our lab. For some reason, they just don't stay in the little pits on the depression plate. I don't know why, but they just won't do it. So we don't have any gases for you to identify. Okay, but they do tend to have very low melting and boiling points. So like butter, for example. Butter's a solid at room temperature, but you put it in your hand and it pretty quickly starts to liquefy, okay, or at least get soft. You put it in the microwave for 10 seconds and it's a liquid. So it's got a low melting point. You put salt in the microwave and I don't know, I've never tried that. Probably nothing happens. Don't try that, just in case it like burned or something. Okay, but it's got a really high melting point. It's probably not going to melt in the microwave. Okay, molecular compounds are not usually as soluble. Okay, so not usually as soluble. Again, butter's a prime example. It doesn't dissolve in water. Okay, oils don't dissolve in water. Sugar does. Okay, but it's not as soluble as many ionic compounds. It'll dissolve, but not as well. Okay, so they're not usually as soluble, and the solutions they form do not conduct electricity. Okay? Alcohol is another one. Alcohol is a molecular compound. It does not conduct electricity. Okay? It's also a liquid at room temperature. Let's say, for example, because this might happen, that one of your unknowns was water and one was alcohol. They're both molecular. They're both liquids at room temperature. Neither of them is going to conduct electricity. They're both clear. How am I going to identify one from the other?
Drink one and wait 1 hour.
No, because you're going to have a really small amount. You should never drink something if you don't know what it is. Just a general rule I have. Okay? If it's something else, you'll die. Yes, it's the if it's something else, you'll die part that concerns me. Okay? You could smell it. Okay? Alcohol has a very sharp, distinctive odor, where water does not. Okay? And that's a safe test for you to do. Okay? Provided you're not snorting it. Okay? You waft it gently. Okay? You don't put your nose over and go. Okay? Yeah, we're not doing that. Right? You don't want to snort any of these because, guys, you're going to have all the compounds in a single depression plate that's only about, that big. That's actual size, okay? They're all going to be in these little pits, okay, like this, depressions, okay? You'll have all the compounds, each one a different one. Some of them will be ionic compounds that might be acidic or basic, and if you were to, let's say, sniff really hard this compound, you might accidentally inhale several other ones, and that could be bad, right? So, yeah, just a gentle wafting. In fact, you probably don't want to do this, the odor test over the depression plate. You probably want to go to the front table where the original samples are and like take the big original sample and waft it. Okay, that'll be the best way to find that. Very few of these compounds are going to have a smell, right? So if one has a smell, it's probably something that's distinctive and important to help you identify it. All right, so this diagram here, guys, is just showing kind of what we talked about before. An ionic compound, or a material, an ionic material, would have an arrangement like this. It's crystalline because of the arrangement of positives and negatives. That causes a crystalline shape to occur. We know that if we put it in water, it'll split into positive and negative. Okay? A molecular compound is going to look like this, okay? Which tends to mean they're not crystalline. They tend to be softer as a solid. Okay? Don't dissolve as easily, certainly don't conduct electricity. They're just arranged differently. Okay? Questions there? Now, molecular compounds which are soluble in water usually produce clear solutions. Okay? I mean, I say clear. It could be cloudy. Like when you dissolve sugar in water, the solution becomes a little bit cloudy, but it doesn't like turn pink. Okay, so they generally produce clear solutions. Alcohol is another example. Okay, if you put alcohol in water, you can't see it. It just mixes right in and it's dissolved. Okay, that's why you can mix drinks if you're a bartender. You can just put alcohol dissolves in all the things you're going to put it in. Okay, so it dissolves in there easily. It's soluble in water. Okay, liquids can be soluble in other liquids if you pour them in and they disappear. Okay, cleaners would be like that. Bleach. Okay, stuff like, well, bleach isn't a molecular compound, but when you pour other molecular compounds in that are liquids, they just dissolve. Some of them. Okay. All right. Questions on that? Okay. How would you know if something if you poured one liquid into another? How would you know it doesn't dissolve? What would you see? Right, you'd see a separation. There'd be a distinct line between the two materials based on their density. Okay? If I pour oil into water, the oil is less dense than the water, so it floats to the top. I can't think of anything that would be more dense, but there are. If I poured a liquid that was more dense than water and it wasn't soluble in water, it would sink to the bottom, and the water would float on top. Okay? So you would see a distinct separation, like a line in the mixture, okay, between the two. Okay. Acids. Now, there's two kinds of acids, weak acids and strong acids. Okay? Ionic compounds are typically going to be, at least the ones we're going to deal with, are typically going to be strong acids. But what all acids, okay, all ionic acids anyway, have in common is that they will shed H plus ions because they're an ionic compound. When I put them in water, they split into the two charged particles, right? Example of a very common acid, hydrogen chloride. We call that hydrochloric acid. It's the stuff that's in your stomach. Okay? The stomach acid in your stomach has a pH of about 2. Okay? It's really good at digesting and dissolving things and kind of eating them up. Right? It has hydrogen in it, and the hydrogen is listed first, meaning the hydrogen is behaving as a metal, right? So this is an ionic compound. When I put it in water, it splits quickly. Acids dissociate really fast. Dissociate means they split into their charged particles. They're highly soluble. Okay, you mix them together and they disappear. Right? Now, it's not like we can get strong acids in their solid form. They're very dangerous in their solid form. Okay, because the instant they touch water, they get really hot and obviously very acidic. Okay, so we don't generally carry them in their solid forms. Right? Once they're in solution, I've got an H plus and then some other ion floating around. The more H plus that an ionic compound can give off, the more acidic or the more powerful that acid is going to be. Right? So hydrogen chloride is a strong acid, but it only has one hydrogen ion in it. Would that be more acidic? Given the same concentration, which one would be more acidic, H2SO4 or HCl? H2SO4. When I put that into solution, it's going to give me 2 H pluses and then some SO4s floating around. Okay, but it's going to give me more hydrogen ions, and the more hydrogen ions something can give off, the more acidic it's going to be. All right, this stuff is really bad. Nitric acid. Okay. Part of the problem with nitric acid is that it vaporizes easily. Okay, if you have a solution of it, it evaporates at a very low temperature. Okay, it's happened to some guys I knew in high school. We were doing a lab where we had this stuff, and we were told specifically, make sure that you always have a top on the flask, because the fumes will come out, and the fumes are obviously corrosive. And unfortunately, the setter on the volleyball team and his partner, the middle blocker, didn't do that. So they were doing their lab, and they were constantly reaching over the flask, doing something, and then coming back and reaching over the flask. And they didn't notice at first, but a few hours later, they looked at their hands, and they were starting to get these chemical blisters all over their hands, front and back, okay? Because the nitric acid fumes had touched and then stayed on their hands and caused a chemical burn on their hands. So now you imagine your volleyball team is without the starting setter and the starting middle blocker because their hands are all bandaged up for several weeks until those chemical burns go away. Right? So very powerful acid because it can give off 3 H plus ions in solution, where the other ones give off less. Here. Hydrogen peroxide is slightly different. It's how does it work? It's H. I'm forgetting the formula. It is acidic, but the nature of it is not a powerful acid. Okay. Now, granted, we get hydrogen peroxide at like 5%. Like if you're getting the stuff that you put on like a cut or something like that, it's like 5%. The stuff that cleans your contacts, I think, is even less than that. Okay. Because we want to dilute it. Right? We don't want to have that stuff in its most concentrated form, because it would be in its most concentrated form very acidic. Okay, but so is acetic acid. Okay, this stuff here. Okay, this is acetic acid. What's the other name for acetic acid? Vinegar. Okay, this is the active ingredient in vinegar, but it's a weak acid. Okay. This is the hydrogen that it gives off. It's not like it's an ionic compound, but it's written the wrong way. Okay, it gives off an acetate ion and an H plus ion. Okay, now vinegar, when you buy it in the store, certainly it's acidic, but again, it's around 5%. Okay, 95% water, 5% acetic acid. We have glacial acetic acid in the lab. Okay, it is basically flip-flopped. It's like 95 to 98% pure acetic acid. You pour that on a surface and it dissolves it like any other acid. It's just based on concentration and purity. Okay, so yeah, that can be very dangerous too. You certainly wouldn't pour this on your fries in its glacial form because it would eat your fries for you. Okay, yeah. All right, so sometimes it has to do with concentration, but I'm saying if I had this acid and this acid in equal concentrations, this one would be more powerful. Okay, this one and this one would be more powerful in equal concentrations. Okay, so acids are ionic compounds most of the time, okay, and thus they share many of their properties. They're crystalline solids at room temperature, they're highly soluble in water, and they are excellent conductors. Okay, most of the time, when you have a strong acid, conductivity. When you have a strong acid, you will have like a conductivity of 10 out of 10. Okay, they just conduct extremely well because, like I said, they dissociate really, really quickly. Okay, acids taste sour or tart. You will not test that. Okay, they do taste sour or tart. Like, I mean, think of a lemon or a lime or something like that, or a grapefruit. Okay, those have citric acid in them, they're tart. Okay, but I don't know what HCl tastes like because I don't want to find out. Okay, you know, if you vomit, that taste is awful, obviously, but a lot of that is because of the stomach acid that you're, you know, refunding. Okay, and yeah, you're getting that sharp taste, and that's kind of a gross thing to think about, but okay, yeah, it is that sharp, really acidic taste because you're throwing up acid. Okay, that's also why it hurts. Okay, like you feel like that burning, that heartburn sensation. That's literally, it's not your heart burning, but it's your esophagus burning because the acid from your stomach is coming up and it's burning the unprotected part of your esophagus. Okay, the inside of your stomach has a lining of mucus. Okay, that's always being replenished, so it keeps the acid from eating your stomach, unless you have some sort of illness where that doesn't happen, and then you get an ulcer. Okay? An ulcer is a chemical burn from the acid in your stomach on the inside of your stomach. All right, and they can be quite painful. Okay. All right, and they will turn litmus indicators to acidic colors. From blue to red, we have universal litmus, which has it changes to 14 different colors. Okay, all the way from 1 to 14. Okay, so the acidic colors are all kind of red, and then they get kind of orangish to yellow, and then they start going to green, and then they go to blue to essentially black being basic. So those will be our that'll be our litmus test. Okay, but acidic colors are generally red and orange. There's also a inside our litmus containers is a chart, so you just put the litmus paper in the stuff, and then you compare it and match up the color, and it'll tell you what pH it is. Okay, and acidic solutions have a low pH, that is less than 7. So if you get a pH that's 4, you're looking at, a weak acid. Okay, if you get a pH that's 2, you're looking at a strong acid. 1, really strong. Okay, things like that. Okay, so like I said, you do have to be careful with acidic compounds, obviously, because they can cause chemical burns. I had a thing happen to me when I was making hydrochloric acid in my early years of my teaching career. I was mixing the stuff and I was diluting it, so I had the concentrated stuff in one hand, okay, and the water in the other hand. And you're always supposed to mix acid to water. Okay, you always mix acid to water because then the water can absorb the heat that is the result of you making that solution. And as I was doing that, I set down the acid, and then something fell from above me, and I reached out to catch it. And when I caught it, I involuntarily exhaled and then sharply inhaled right over top of the hydrochloric acid container. Okay, and a colleague found me on the floor. Okay? And they were freaking out when they saw me because I had inhaled this stuff through my nose, and when they found me, I had blood running from my nose and down my face and onto my neck, and I'm laying there on the floor unconscious. Okay, because I had inhaled this stuff, and it's just because it got into my sinus cavities. It was an automatic kind of spinal reflex to knock me out. Okay, and obviously it had given me a nosebleed on the inside because it burned away a little bit in there, and yeah, it was kind of ugly, right? But you do have to be careful with this stuff. And I have a tendency to make sure that when I mix stuff, that I mix it strong. That way it works, okay, and it does the stuff we want it to do. So you have to be mindful in the lab that some of the stuff is harmless and some of the stuff isn't. Since it's all unknown to you, you have to treat it all like it's dangerous. Okay? All right, questions on the acids? Okay. Bases. Bases are also ionic compounds, at least the strong ones are. Okay? Not all bases are ionic. Weak bases can be molecular. Okay? Bases are ionic compounds, and usually their solutions will conduct electricity. Okay? Because they're ionic. Now, typically bases taste bitter and will turn litmus indicators to basic colors. That is, in the blue part, okay, of that. Again, we're not going to be doing any taste tests, okay? But things that would taste bitter as a result of being basic would be things like soap. Okay, soap tastes bitter because it contains lye, which is a really strong base. Okay? That's how they make soap. Drawing a blank on other bitter things, but anyway, okay, yeah, they'll generally taste bitter, but we're not going to be tasting them, so it doesn't really matter. Now, all bases contain hydroxide ions, one of our polyatomic ions that we talked about the other day. Okay, they all contain these, okay, like this stuff. We talked about it yesterday. Sodium hydroxide. Okay, very powerful base. It's in oven cleaner. Okay, we'll use it quite a bit. Okay, there'll be several labs where it'll be involved. But anything that has that OH ion in it, when it hits water and goes into solution, it splits up into whatever the metal was and OH. Okay, and that OH will make the solution very, very basic. Okay, so basic solutions have a pH that is higher than 7. They're going to be, yeah, generally less extreme. There could be some that, like you could have a molecular base that would have a pH of like 9 or 10, right? You could have a molecular acid that could have a pH as low as 3, okay? But generally they're not going to be on the 2 extreme ends. Yeah. All right, now, what's this compound? Hydrogen hydroxide. Does it have another name? How many hydrogens does it have in it? How many oxygens? It's water. Water written as an ionic compound, but it's still water. What does it contain? The most acidic ion, the most basic ion. Water's pH is neutral. Okay, it's got one of each. right? It's got the most acidic, but it's got the most basic. They cancel each other out completely, okay? And water has a neutral pH as a result. Okay, questions on the bases? Okay, all right. That's all that we needed to cover. Went a little quicker than I thought. So let's finish up the naming stuff there, guys. Okay, and then tomorrow we'll talk about how to do lab reports, what kind of things are important, and we'll start on writing up your lab report for Monday.